I gleefully stole these slides. The backstory here is I got an email from one of the co-organizers of the LA Scalability meetup, basically saying, "Hey, I got this email. Would you be interested in presenting at the South Bay JVM users group?" Like that was a few days ago. And so I said yes, but since this is a different presentation than the one I gave to the LA Scalability, High Scalability meetup, I had to very quickly try to address the question of why Scala from probably the perspective appropriate for folks who are more familiar with Java. So I didn't already have a presentation along those lines, so I had to quickly find one that I thought communicated all the points that I want to communicate, and this is the one that I found. So hat tip to Adam. These slides are online. I can send a link out to everybody who would like a copy. I'm sure Adam would appreciate that. They're a couple of years old, but I think they still are relevant with the current version of Scala. So anywho, moving right along, Mark Notersky, 2003, got a little frustrated with the state of Java, and he had a right to. He wrote the last 3 Java compilers, Java C compilers, and in particular implemented generics in Java 5. That implementation didn't go exactly the way that his original design had gone, and so that was one of his frustrations. And so one of the things that came out of that was finally the question, after doing 3 versions of the Java compiler, should I keep trying to improve the current state of the art, or should I just break with the past? And JVM is a great platform. We all like JVM, but Java the language, does it still have legs, and is it time to make them long? Scala stands for Scalable Language. That's frankly to me a little bit of a joke, in the sense that it's actually the Italian word for stairs. that's actually where the name comes from. But some folks like to say scalable language, and that's fine, I suppose. One nice thing about Scala is that it does have a REPL. For those of you who are familiar with some of the dynamic languages, I guess you use Groovy a lot, so no question you're familiar with the idea of just typing in code on the fly and trying it out. You can totally do that in Scala. Just type Scala and start typing in stuff and taking it for a whirl. We see a little addition here, some set containment operations and things of that nature on the command line.
So can you also type Java code in that shell?
No.
Oh, no?
Well, yes and no. Some of the slides coming up will talk about that. Okay. It is a JVM language, so can you exercise Java APIs on the fly from the Scala REPL? Yes, you can. And in fact, in terms of, if you want to think of that as a gateway drug, like if it, Scala, just put the jar file out there and it works. You shouldn't actually do that. But what you can do is encourage your organization, if you're interested, to, for example, start using one of the Scala testing frameworks like Specs2 or Scala Test or Scala Check to develop your tests, because I think there are some clear benefits to the Scala test frameworks over JUnit, TestNG, that family of tools, and that's a great gateway drug for getting the organization into Scala, if you're at all curious. Scala is object-oriented. It has everything you expect in an object-oriented language, class-based object-oriented language. Classes, interfaces, fields. Scala is maybe a little different, certainly different than Java, in that everything is an object. Absolutely everything is an object, and I'll talk about that a little bit more in a minute. We have traits, which are an improvement on interfaces, and we already saw an example of singleton objects, but we'll talk about that a little bit more as well. So, basic stuff. You define a class called account. It has a variable for the balance. It has a couple of values for the owner and for the withdrawal limit. And we have a transaction log that we use to log things that are going on with the transaction. Methods for get summary and withdraw. Simple stuff, obviously if statements, you know, if, else, addition or concatenation for strings and floating point values, comparisons, you know, less than, and for Boolean and, of course. All very familiar sort of stuff. Maybe slightly syntactically different with the def for method definitions and, you know, things like that. Nothing too outrageous. There's good old private, you know, nothing wild. So the account definition, you know, class with a name, your field declarations are in there. They can be variables or values. Values are like final. Basically, they can't be changed. And again, you define methods with def. Still nothing terribly shocking going on here. Yeah, var, val, again, var means variable, readable, and writable. Oh yeah, this is important to point out. We don't define getters and setters in Scala. The language does that for us. There actually are methods that the compiler creates for us to do getting and setting on vars, and only a getter gets defined for vals. And what else is interesting about this? Oh, construction. In Scala, the class constructor is the body of the class. So when you see tx_log.log here, that's actually called at construction time when you say new account. So that's how Scala handles constructors for a class. And I'll talk a little bit more about what I mean by for a class a little bit later. Method definitions, you know, again, nothing too terribly mysterious going on here, but because we do have vars and vals, it might be worth pointing out what's actually going on in this code here, for example. So as you can see, account.currentBalance, when you say equals on that, it actually calls the setter for that var. It calls the getter when we ask for the account.currentBalance. That all happens automatically under the hood. Account.accountOwner equals whatever. That won't even compile because account owner is a val. So it would be like trying to assign to a final compilable line.
Well, you said the thing said it's not immutable though.
Yeah, it's not recursively immutable. So if you have anything that is mutable in the thing, like you've got this object and you assign it to a val, then yeah, you can mutate whatever is mutable in the structure or in the object that is assigned to that val. So yeah, good catch. Here is the essentially equivalent Java code. As you can see, there's quite a bit more of it to reproduce all that behavior that you get from this. So I mentioned a little bit earlier, everything is an object, and actually everything is an object. Scala has no operators. That freaks people right out most of the time. I'll explain a little bit more about what that means. It has no primitives, but don't worry, you're not going to get totally screwed by boxing and unboxing of objects, because the compiler actually optimizes cases that could be primitives to primitives as far as the JVM is concerned. But you don't have, at the language level, the source code level, you don't have this dichotomy between int and integer. This says no arrays. That's a bald-faced lie. I have no idea what he's talking about. Scala absolutely does have arrays, and they are Java arrays, just like their strings are Java strings. No statics, that's true. We just have objects instead of static array. Inheritance, it's object-oriented. Of course we have inheritance. So we have a fruit trait here. Again, trait is our moral equivalent to interfaces with some extra features that we'll get to in a minute. Class apple extends fruit, blah, you know. Granny Smith apple extends apple. Nothing novel going on. Okay, traits. Interfaces with implementation. One of the things I always hated about Java is that, we all know multiple inheritance is a problem. Their solution to that problem was not to let you put any behavior on interfaces at all. Scala lets you put behavior on traits if you want. So they're like a cross between an abstract class and an interface. What you can't do is construct a trait. And that's how you avoid the time and the death inheritance problem in Scala. So they solve that problem a different way. And yeah, special considerations. No initialization of fields with constructors, special meaning of super. Yeah, in super, because you know, an interface, you don't have multiple inheritance, so you statically know what super of an interface is. In Scala, you can have multiple traits mixed into a class. So what super is, you don't know until you mix it into something else. Yeah, so traits are used a lot to factor out behavior that doesn't make sense to instantiate. It doesn't stand alone. It has to be combined with something else. It's essentially a David knows flavors and mix-ins and all that kind of stuff. So it's a lot like mix-ins in Ruby or any other language that has mix-ins, basically. You can compose arbitrary collections of behavior into a single end structure or object. Rich interfaces, yeah, this is a nice example. So you can have a trait called comparable that's parameterized. Scala uses generics a lot if they actually work in Scala, unlike Java. So this trait is parameterized by a type A. We don't know what the type A is, but there is one. And we say that you can compare the current thing to some other thing that's also an A, and you get an int out of it. And then we define some methods that actually, depending upon what this int is, tell you whether it's less than, equal to, greater than, or less than. And there's a note down here that makes a pretty important point. Notice that you can use characters like greater than as method names in Scala, and in fact you do all the time. Because again, Scala doesn't have any operators. All it has are methods. So you'll see what that. I'll either show or tell. I can't remember what some of the future slides say about this, but I'll explain that a little more later on.
So in that case, I'm sorry, so the less than, greater than are all like methods, treated as methods?
Yes. However, and we'll see this. Well, actually, we see it already in this slide. If you look at this, compare that, notice that there aren't any periods there. And notice that there aren't any parentheses around that. So one of the things that Scala has, instead of having operators, what Scala has is dot and parentheses inference. So you could actually say this dot compare open parentheses, that close parentheses. That's actually what this compiles to under the hood. There's a small set of rules that's page long, probably worth committing to memory, but I haven't, with respect to how dot and parentheses inference works. It's pretty straightforward in the case where you've got a method that takes a single parameter, for example. You just blow off the period and the parentheses and it works fine, like this compare that in this instance. So when we define these methods that have these kind of operator-like names, go ahead and use them as operators when they're defined on the object to the left of the method name.
You said as no operators, but you're using the equal sign as an operator there.
Right, so that's a method, actually.
So it's a predefined method.
Mm-hmm. Oh, I'm sorry, you mean define whatever Boolean equals?
Yes.
That's part of the method definition syntax in this case. But when you say 1 equals 2, for example, you're literally saying 1 dot equals open parentheses 2 close parentheses.
Oh, I see.
Equals is a method on the end, or string, or all sorts of stuff. Right? Mix-ins, yeah. So this is kind of another neat example. Trait no null access map KV extends Java util map KV, and it overrides the get method in this case, and basically says, if the thing you get back is null, then below this assert, otherwise return the value. Similarly, no null access map sort of does the opposite way. Basically says, oh, sorry, that's the next slide. Yeah, here the point that he's making is that this get method is abstract. The exact functionality you're overriding is not known at compile time here. And then no overwrite map is at the opposite end. Basically, if the key already exists, then deny the quit. And then you can mix both of these into a class. So you can say with no null access map, with no overwrite map, and mix both of those traits into your class that extends hash map, in this case, to add that behavior. In this case, you'll be overwriting both get and put to disallow nulls.
Can you go back a slide?
Yep.
So you're extending map here, but it extended hash map. Go to the next slide now.
Mm-hmm.
He's actually extending hash map.
Yep. Hash map implements the map interface, right?
Right.
And so our modification of get and put, we don't care what kind of map it is. Get and put work on
any map.
On any map.
Right.
Yeah.
Right. Okay.
So, but when we mix these traits in, we have to mix them into a concrete.
The concrete.
Yeah.
So even in the previous slide, even if you didn't extend map, you could still, like
Yeah,
if you
you
didn't
could still
extend
use
map,
those
you could
traits.
still use that trait on the other one just because the signature matches.
Yes.
Okay.
Yeah. Yeah. You could extend any other kind of map that supports that. Map is the interface that provides get and put.
Yep.
So that works. You can also say, give me a new value and say it's a new hash map, and I want this new hash map to mix in no null access and no overwrite. So you can do it on an instance basis as well as a class basis. That might be the thing that is most different so far about Scala relative to some of the other languages.
That's pretty sweet.
Yeah.
But isn't that in just kind of doing expand the meta kind of stuff in the Groovy world?
Yeah, something like that. Yeah.
Yeah. Yeah. Very similar to that.
But even shorter syntax, I guess.
Maybe. Yeah. Pick and choose characteristics for individual map instances. Yeah, that's pretty cool. So you see this a lot in the Scala world, where people are, at least when people have been fairly careful about factoring separation of concerns. You have a class that extends some base, either trait or class, and then mixes in an arbitrary number of other traits to actually compose the functionality into one, into the class that's being created or declared. Yeah, so this raises some interesting design questions. And this literally is just food for thought. There's nothing deeper to try to answer here. If you have traits, when would you choose inheritance and when would you choose composition to model a solution to your problem? Singletons, again, you have objects and they are objects. You just go ahead and say object and then you do whatever you want to do with the object, just as if you had set new on a class. Simple. Yeah, these are the reasons to appreciate them. Particularly significant to point out, thread safe instantiation. It is. You create the class and boom. You can do that in a thread and it's perfectly fine. Objects can extend traits or classes. That makes them pretty handy too.
What's the scope of object? Is it basically, can I grab checksums in some other class?
Yeah, totally. So it's exactly as if you had said,
static.
Yeah.
Like a static initializer block in Java.
Well, or you had said whatever, pick your favorite singleton construction pattern, and then you assign that to something called checksum.
Right?
Yeah. So think of it as sort of like a final get instance. If you say final whatever type equals get instance on some factory class or something like that. It's ridiculously straightforward. You'll wonder how you ever live without them. And yeah, Scala is fairly consistent with Java in terms of simple OO concepts. We've now seen most of them. Classes, fields, polymorphism, and goes a little bit farther with traits, which are an enhancement of interfaces. Everything is an object, and the uniform access principle, again, the getters and setters being generated for you, called automatically, generated automatically, you don't have to think about them.
I assume you could override them.
Absolutely. Yep. Yeah, so they follow a naming convention. So if you do have to deal with code, like using reflection, for example, where you need to know, you need to get access to the getter, you need to get access to the setter, you absolutely can. Scala is functional. This is probably the big, if you were to ask Martin what his big design goal was, it was really to come up with a usable combination of an object-oriented programming language and a functional programming language. So functions are first-class citizens. We have anonymous functions, lambdas. They're not called lambdas, but we have them. There's a heavy emphasis on immutability and lack of side effects. I guess you guys heard from the Clojure community recently. They have exactly the same emphasis. I like to think of Scala and Clojure as the statically and dynamically typed sort of kissing cousins. They both have this common DNA of functional programming, emphasizing immutability, and then one happens to be statically typed and the other happens to be dynamically typed. We have really nice pattern matching capabilities. I'll show you that in a minute. And type inference. This one's kind of a must-have for me at this point. I've been programming in some other statically typed functional languages for a while now. And let's be honest, nobody likes to say, capital foo equals new capital foo, open parentheses, close parentheses, whatever. That's just ridiculous. So with type inference, thankfully you don't have to do that. You can just say val foo equals foo, or new foo, as the case may be. Imperative programs consist of statements that change state. I think this is pretty basic stuff. Functional programs evaluate expressions and avoid using state and mutable data. Functional Scala. Functions are objects. That's true. So here's a definition, just a bare definition of a square function that squares an integer x. Under the hood, what Scala C generates when it compiles that looks like this, basically. There is a class called function1, which tells you what argument the function takes and what type of argument it takes, what type of argument it returns. And then it has an apply method that takes the argument and then the body of the implementation. That is literally what the compiler generates when you say that. And here it is, val square function equals, open curly, x, which is an int, goes to x times x. That sort of arrow there is our answer to lambda. So basically the curly, you have the curly, then you have the parameter and the parameter's type. You do have to declare parameter types. That's one area where you don't have type inference. And then the body on the other side of the arrow. And as it says, it's just shorthand for that function one definition that the compiler generates for us.
Isn't Java 8 going to follow a similar syntax?
I think I haven't looked that closely at the Java 8 lambda syntax, but I think it is.
I think I'd seen that it was followed.
Yeah, I think that's true. To be honest, I haven't followed Java in a while.
I accidentally came across that.
Yeah, it's funny. I mean, now that I've been programming Scala professionally for a year and a half, like so far, the argument to apply becomes, the argument to the square function, and then x times x is x times x. Here's some lovely Java code to cycle through a list of city names and find names whose length is less than 8. As you can see, it's the sort of hairball that we all know and love from our Java days. In Scala, it can look more like this. Here we have a list of cities, and if we want the short cities, we just filter the cities using a function that looks at the length to see if the length is less than 8. Filters, awfully handy. That can be even more concise. We can just say short city equals cities.filter and then pass this function that takes the city and checks to see if its length is less than 8. That's not bad. We can even do better. We can say underscore for the argument to this function. And underscore just literally means the argument that's passed to the function, whatever it is. And because we already know that cities is a list of strings, type inference takes care of figuring out that the type of that underscore is a string. And so the length method exists, and it'll compile and it'll work. And it works fine. And so, here's the comparison of the functional style and the imperative style, and a little comment to the effect that you can sort of look at this at the Java code and see where opportunities for defects tend to show up. I think everybody here is probably.
In fact, there's one in that code.
Yeah.
They forgot to close the
Yeah.
string under cities.
Yeah, exactly.
Yeah.
So, right. And that's, these next few slides are all about sort of pointing out how too much code is just an invitation to those kinds of defects. Putting the fun back in functions. So here's, I mean, Groovy developers are not going to be terribly impressed by this. But of course, we have, like any other modern programming language, we have multiple assignment. And we have this nifty partition function on lists that basically takes a predicate and partitions the list into two sublists according to the predicate. So it's kind of nice. It's certainly way better than Java, not terribly surprising for users of other languages. Here's a nice example of a map where you can basically say, given a list of things that have some property, turn that into a list of the values of that property. So we map over the list of employees and get the salary. Now we have a list of salaries, and then we can call sum on that to get the total of all the salaries. And similar sort of thing here. We can update a counter, and then when somebody clicks a button, there's some code here. Again, the arrow, sort of equal sign, greater than sign arrow, means that this is a function that happens when this case happens to be the case. Custom control structures. That's a little highfalutin. With first-class functions, with lambdas, as I think probably everybody, like Groovy developers know, you can write functions that take functions and do important stuff around them, like transaction management. So this is just an example of that. Here's your basic try-catch block around starting a transaction, doing something with the account, and then making sure that the transaction is closed regardless of what happens. Or does it? See the little yellow post-it note again. Where's the bug? Because there is one. T could be null. T could not have been successfully acquired by the time you get down to the find that block. Wouldn't it be nice if you could find that bug and fix it once, and not do that on a sort of per use of transaction kind of basis? So wouldn't you like to be able to say something like this? Transfer the money from one account to the other account in a transaction. And you can, that code actually works. And of course, again, folks who are familiar with lambdas and higher order functions, this is nothing new. For Java developers, it might be new. The idea here is that we have a function transaction that takes another function as its argument. And in this case, it's just a function that doesn't take any arguments and doesn't return anything. Unit is essentially the same thing as void. And so here is exactly the same code with respect to the transaction management, but instead of actually manipulating the account, we now just call the transaction code that was passed in as the argument. And of course, we check to see if the transaction is null before trying to close it. So we only have, if we had the bug, we only have to fix it in one place. And it works, of course, for every invocation of the transaction function on some other function that actually does what needs to be done in the transaction. So, why first-class functions? Move boilerplate to a library, less bookkeeping, fewer mutable variables. If you put all of your important sort of state management in a higher order function, then it's in one place, and at least when it gets fixed, it's fixed everywhere, and so on. This is a nice quote from Mark Pellegrim. It's actually about Python, but it makes a sort of a general point about functional programming and about using higher order functions like filter and map, which is basically that if you don't use them, then you might as well be programming in Visual Basic. And with all of the sort of hiccups and tendencies to defects and so on that implies. There really is, and I can tell you this from first-hand experience, and some of you, I think, already have had similar experiences. The arguments in favor of functional programming, and I'm going to take off my Scala hat and statically typed hat and all that kind of stuff. The benefits of functional programming over imperative programming and imperative object-oriented programming in particular are very real. They're very real. You can reduce your defect count a lot by taking advantage of higher order functions and first-class functions. What else is significant about Scala being functional? Emphasis on immutability and lack of side effects. What's wrong with side effects and immutability? Well, think about what you hate about the code that you hate. Lack of separation of concerns, variables changing from multiple places at multiple points in time. It's hard to just look at the code and know what it does because you might not know what the state of the system is at the time when you're just looking at the code in your editor. Control flow tends to be all over the place. Mutability is surprising. Once again, here's some code, some UI code that has a bug, and it can be a little difficult. Even in just, what is this, 5 lines? It can be a little tricky to figure out exactly why it is that that you get null out of that system.out.println. If you want to study it, you can. Again, I'll make the slides available later. I don't know that I want to take the time with it right now, or that we should take the time with it right now. Mutability has unintended consequences. I would argue that that's what mutability is. It's an unintended consequence. It just makes it hard to understand what even these little snippets of code are doing. You can't just look at them, glance at them, and have really high assurance that you know what the outcome of executing that code would be. Mutability is hard to maintain. I worry about anybody that I need to explain that to you, to be perfectly frank about it. I think everybody knows at this point that mutability is hard to maintain. Side effects can blow your mind. This is probably my favorite slide in this entire presentation. This code doesn't have any obvious defects, but nevertheless, it is item number 13 in effective Java, and it does in fact have a bug, and it has to do with the unexpected side effects of data parsing. Yeah, it's once again, it's not a lot of code, but it's wrong, and it would be easy to write this wrong way. I mean, it's the key thing that I take away from this. This is perfectly reasonable. There's there's no boneheaded forgetting to check for nulls or something like that. It's way more subtle. So, why immutable and side effect free? It's easier to reason about. You don't have to worry about what your callers are doing to your data because they can't change your data. That's the whole point. And the truth of the matter is, we live in a multi-threaded world. The world in which you could get away with slapping a synchronized block around everything, or synchronizing the entire method, or synchronizing an entire class. We all know that kills your scalability, and you just don't want to. There are too many instances in which people sort of reactively put synchronized around something to solve a concurrency problem, and they're not really sure that it'll solve the concurrency problem. Maybe it does, maybe it doesn't. You run the code again, it works that time, you pound on it for a while, and you put it into production. It's no way to live. Scala and Immutability, again, val versus var. To me, var in Scala code is a code smell, but every once in a while you kind of have to go try to use val. The collections library, again, we have map, filter, reduce, fold, all that kind of stuff. So there very rarely is any reason to use mutable collections. And as far as concurrency goes, we have actors. We'll talk a little bit about the Scala actors library, but that's changing. Akka is becoming the standard for actors in Scala. So here's a class. It just has a couple of val fields, so it's immutable, first and last, to read only. I'm not sure I agree with this terminology. Val does not mean immutable. Yeah, it does. Immutable never, ever meant that there was a guarantee that all of the fields in the object are immutable. It just means the variable that contains that object is immutable. But if for some reason you need your entire object to be immutable, then you have to use vals all the way down recursively, which is a good thing to try to do. The Scala collections library is divided into two parts, mutable and immutable. Scala is not Haskell. Scala is not a purely functional language with no side effects. You can have side effects if you want. We already have var, and there are mutable collections as well. But when you write Scala code or when you fire up the REPL, if you just say, for example, list open parentheses, whatever set of elements, close parentheses, that list will be immutable. It's immutable by default. Yeah, so actors are the preferred concurrency model for Scala. There's no runnable, there's no synchronized, there's no locks, there's no shared mutable state. The model is taken from Erlang, for those of you who are familiar with Erlang, and RabbitMQ is written in Erlang, so it's got a long history of working as far as scaling concurrent software and that sort of thing is concerned. And that's in fact where Akka is directly inspired by. Akka is essentially the Erlang OTP for the JVM. The Scala actors basically look like this. You can declare an object that extends actor, and then you define how it acts when it gets a certain message, and that's what those case statements are. Those are basically looking to see what kind of message the actor got and what to do when it gets one of those messages. And so you send a message with bang, with the exclamation point method, and simply send a message to an actor, and the actor will respond to it. Again, no synchronizing, no shared mutable state across actors. You certainly can have state in an actor, but it's invisible outside the actor. The only way an actor does anything is by responding to messages. So, things to think about if you're using Scala. What effects does immutability have on performance, and what effects does immutability have on correctness? Again, I can tell you right now, just from a hard-nosed practical standpoint, and again, this is not specific to Scala, it's about immutability. It makes a huge difference to correctness. Most of the defects that I've ever chased down in my JVM language-based career have had something to do with the system being in a state where some variable was changed out from under something unexpectedly. I mean, that's 90% or better of the defects that I've ever dealt with. Pattern matching. This is really cool. Pattern matching is a switch statement, yes, but it's way more powerful than the switch statements that we're all familiar with. Matching the properties of object graphs, not just ints. That's a biggie. You can match on objects type, so you can check to see if it's a string or an int or a float or whatever. You can extract values from objects that you're matching against. And if you miss a case, the compiler will at least warn you about it. Or worst case, you'll get a runtime exception match for you. So, for example, here's a definition of a Boolean parsing function that will take anything and try to make sense of it as a Boolean. And as you can see, it's matching the input A against several different types. If it's already a Boolean, it just returns the value. If it's an int, it checks to see if it's equal to 1. And if it's a string, it checks to see if it's one of those 3 strings that are in that val at the top. So there's a good example of matching on the type of the value that's sent to that function. Pattern matching on case classes. Case classes are a special kind of class in the sense that they're sort of predefined value type classes. You just give them a name and you name all their fields, and that's it. And that's nice because they give you things like equals and hash for free. They also give you this pattern matching support for free. So you can match on a person, and you can, as you can see, you can say, I just want to know if the last name is Smith, and I want to know, if they're in Virginia, and I want to know what town they're in if they happen to be named Smith and they're in Virginia. So there you're extracting the town from this person object that you're matching against. And the case underscore basically means that's the default. That's the fall through default case. And yeah, for representing your data objects, again, you get an extractor for free, equals and a hash. Oh, and you get a reasonable two-string implementation for free as well. You also get a copy method. And so with named arguments, that turns out to be really handy. So you've given an instance of a case class. You can quote unquote change the value of one of its fields just by making a copy of it and saying, whatever field you want to change equals whatever you want the value to be. So you're not actually changing it; they're immutable. You are copying it and then creating a copy with one field or however many fields that are different from the thing you're copying. So there's a lot going on with case classes. Again, if we look at two-string, hash, equals, extractors, if you were to try to express this in Java, it would look like that. So there's a huge amount of stuff that case classes give you for free relative to Java. Yeah, there's that. Type inference, we talked a little bit about this already. You have type inference for local variables, the return type of functions, and type parameters. Again, semicolons, oh right, I forgot to mention, semicolons, you might not have seen a lot of semicolons in the code. Those can be inferred most of the time too. Dots, braces, parentheses. There is a return keyword in the language, it's hardly ever used, you don't need it. The return value of any method is the last expression in the method, so it just returns the value of that. Everything in Scala has a value. There are no statements in Scala. It's an expression-oriented language. Absolutely everything has a value, including if and things like that. So that's why I don't tend to see return a lot. How does type inference affect readability? Well, if you remember some of the partition and so forth kind of things we saw earlier, it tends to turn a lot of things into one-liners or two-liners. It's very effective in noise reduction. The option type, this is to me the gateway drug into Scala. I'll show you a little bit more about that in just a minute. Implicit conversions. Implicits are controversial, but Scala has this notion of implicit definitions or implicit objects. And basically what that means is if they're in the lexicon, you can have either objects or functions or methods that are in the scope, in some lexical scope. And if there's a need for something as a parameter to something else that you don't currently have a value of that type for, but you have, for example, an implicit definition that will convert one type to another type, that implicit conversion will be used to fulfill the type requirement for the thing you're calling. Named parameters and default values, we saw some examples of that before. You can have named parameters to methods and then you can have default values. That's pretty handy. So here's yet another spot the bug. Right, and I think we've probably all heard this sort of thing before, right? Get person can potentially be null. Person 1, 2, 3, 4 might not exist. How do you know when a value is null? This is ID expected. Then you return some, you wrap some around the value that you want to return, otherwise you return none. So option is basically an abstract base class that has two subclasses, some and none. And some actually has a value associated with it. And that's basically it as far as what an option looks like. What you can do, yeah, there you go. Extended by some and none, encodes optional values. Type inference helps keep the noise associated with it to a minimum, and it actually works out really well. So you can either call get on an option if the option doesn't actually have a value. If it's none, that'll throw an exception. There's a get or else method. So if you have a default value that you want to use if the option doesn't have a value, you can do that. And options also work really well in pattern matching. So you can match on some and do whatever you need to do with both of those cases. What's especially nice about this, and I don't think, yeah, he doesn't have a slide for this. To me, the author of these slides missed maybe the most important feature especially for Java developers. And that is that if you wrap an option around a null, it constructs a null. And what's really super cool about that is, remember, some and none are types. They're not special values, they're types. And so, for example, if you use this pattern matching construct, case some, case none, and let's say you forget to put in the case none, you'll get a warning from the compiler. And there's a compiler flag that turns warnings into errors. So you can actually eliminate all of your null pointer exceptions just by wrapping anything that could potentially return null, wrap it in an option, and then turn on the compiler flag to turn warnings into errors. And the compiler will tell you if you forget to handle the none case. Or for that matter, if you forget to handle the some case. But you can turn NPEs into a thing of the past. And that to me is reason enough to use Scala. Why he didn't put that in here, I don't know. Implicit conversions I've talked about a little bit already. Basically, you can use them to either convert types to other types, or even more interestingly, you can extend the behavior of a type by converting it, implicitly converting it to a richer type. That is a subtype of the type that it's converted. So you still have all the old behavior, but you also have a whatever range of new behavior the converted to type has. So for example, I mentioned that Scala strings are a Java long string. That's true. But Scala also has implicit conversions of string to a type called rich string that has a bunch of functionality that Java strings don't have. And that all happens automatically under the hood when you use any of the methods on rich string. It automatically converts the string to a rich string. Yeah, and so here's an example using int. If you have a class called rich int that adds a times method, and yeah, here's what you would have to do to use it directly. New rich int 5 dot times blah blah. So no, that's not too bad. So you can introduce an implicit definition that converts an int to a rich int, and the implicit definition just literally says new rich int around the int, and then you can say 5 times print line a, and that actually works. So you can take, and it's nice because you can take advantage of the dot inference and in parentheses inference, and you can actually construct embedded domain-specific languages this way and do some fairly sophisticated stuff.
So what happens if someone else has defined a times method and an implicit?
If there's more than one implicit that defines the same conversion, the compiler will complain about an ambiguous implicit resolution. And then you can do one of a couple things. Either make sure that you don't have 2 implicits in the same scope, so it's not ambiguous anymore, or you can disambiguate in your invocation of whatever the method is. So whichever is most syntactically pleasing, I guess, would be the best way to put it. Name and default parameters, again, nothing too mysterious going on here. Just go ahead and name your parameters. And if you want them to have a default value, then go ahead and assign them a default value. That works wonderfully. And so here's an example of send mail. Sometimes you have these APIs, right, that can reasonably take a fairly large number of parameters, but they can also equally reasonably not want some parameters. They can have reasonable defaults, and it's nice to have named parameters and default values in those cases. So that's, there's a whole. This is scratching the surface, believe it or not. All of these are absolutely true. Domain-specific languages, great support for domain-specific language construction. Same generics. We talked a little bit about method names that look like operators, or even weirder things. Multi-line strings, quote, 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 will let you start a string that can span multiple lines or contain special characters, like quotes, for example. Structural typing. Think of it as statically typed duck typing, where basically a type is defined by the operations that it supports completely. So it's almost a workaround around static typing. XML literals, you can actually, in Scala, you can say open bracket, whatever, close bracket, blah, 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 in your source code, and that actually constructs a node tree I forget what the actual name of the
DOM.
type. Yeah, there's a type in the Scala standard libraries that represents effectively a DOM tree. So in web code in Scala, you can actually see that quite a bit. Currying, partially applying functions, again, for those who are familiar with higher order functions from other languages, it's not necessarily new, but for Java developers, it might be pretty novel. This author's favorite 10 aspects of Scala, Java interop, no surprise. Concision and type inference, that's probably one of my favorite things. Functions as objects, absolutely. Some non-option, that's my number one with a bullet. All by itself. I think I would have converted. When I learned about option, and in particular when I learned about option around null becoming none, and that's a type, not a value, that I think would have sealed the deal for me all by itself. Implicit conversions, traits, wonderful collections library. In fact, in the current version of Scala, you can take any collection operation, any of the higher order functions like map, filter, all that kind of stuff. And if you take the collection name and say .par before the operation, it will do that operation in parallel. So you have parallelization across multiple cores on the collections library for free. Default and name parameters, case classes, a REPL, interactive development, type and go. Here's where I get all philosophical. I was a dynamically typed language fan for decades. I was a Lisp programmer, scheme programmer, all this kind of stuff. Mostly because I loved being able to just type stuff in and try it out interactively. And I was under the impression that statically typed language meant that you had this edit, compile, link, run, crash, debug cycle inevitably. Turns out not to be true. Turns out the only languages these days that don't seem to have REPLs are C, C++, and Java. Why that is, I honestly don't know. But at this point in time, that fact alone is a plenty good enough reason never to use those languages again. These concepts are embedded statically typed JVM languages too. Yeah, that's true. Phantom goes to, I don't think I've ever heard of that one. Java 8, again, these slides are a couple years old, so late 2012.
13.
Yeah, exactly. 2013. So there's also, of course, nowadays Kotlin and Ceylon, right? And Kotlin and Ceylon I feel compelled to mention because from a political perspective, they've pretty clearly, and in some cases, in fact in both cases I think even explicitly, been developed somewhat in reaction to Scala. Scala has in certain circles a reputation for complexity. You can certainly write complex Scala code. I sometimes do write complex Scala code. So Kotlin and Ceylon try to provide some of the benefits of Scala without some of the complexity real or perceived. One example of that is their support for nullable types. Phantom is a good example of that, by way of comparison to the option type. And one of the things that I really like to point out about Scala and option, by way of comparison to Phantom, and I think Ceylon has the same issue, but I'm not positive. Option is not built into the language. Option is in standard library. You could have written option yourself. So the thing that I like about Scala in that regard is that it is a rich enough language and a powerful enough language that you can implement things like option yourself. And that turns out to be hugely important when you start tackling much bigger and much more complex issues, like the way that I talk to SQL databases from Scala is with a framework called Scala Query, which is in Scala 2.10 evolving to a new framework called Slick, which is strongly inspired by Link from the Microsoft language like C#. And the point there is that it's a general purpose relational algebra library that you can use to query collections in memory or SQL databases externally with the same syntax. And the syntax for queries basically is for comprehensions. And actually, we didn't even talk about for comprehensions here, but Scala has them. It's basically for open curly, whatever left arrow from whatever on the right of the left arrow, which acts like a container. And then you can have as many of those as you want. You can have guards on them, and then you can either yield or do something that has a side effect after the closing curly on the 4. That's actually syntactic sugar for a sequence of map, filter, and flat map. And so you can define your own types that have those methods, and if those methods have the right relationship to each other, then your types can be used in for comprehensions as well. So what some developers have done is taken advantage of that to develop these relational algebra mappings from for comprehensions to the database. So the for comprehension constructs the SQL, and then when you ask for the results, like you say list on what gets yielded, then it actually takes the SQL query, sends it off to the database, sends the results back, and then constructs the in-memory result from the results out coming back from the database. So it reads like ordinary Scala code and has all the type safety benefits of Scala code, and doesn't risk SQL injection attacks, doesn't risk constructing bad SQL because you're not just putting a string with a SQL statement in your code or anything like that, and it's just pretty nice. And all of that is because the language allows you to do stuff like, this powerful, to define these kinds of types yourself. Don't be fooled by how much the standard library stuff looks like language features. The Scala language itself, without the standard libraries, is actually quite small. The spec is actually smaller than Java. It's a simpler language than Java. That tends to fry people's minds. But it actually is a simpler language than Java. It's just that it's a more general and powerful language than Java. And so when you start taking advantage of it, it can be confusing at first. And there's definitely a learning curve to it. I don't want to overstate the case. But the complexity argument tends to break down once you actually start to understand the difference between language feature and what's provided by the standard library, or what's provided by a third-party library, that you could actually understand. You could have written it yourself. It's just a question of how much study are willing to put into it. So let's see. Yeah, that's essentially it. Scalalain.org is the main site for Scala. Simply Scala.com, slightly out of date, but still kind of cool. And again, I found these slides online. The author was kind enough to make them available. I thought they were a good slide set. I didn't feel like I had to add anything really other than the comments about option and null really is the most important thing, and for comprehensions, I suppose. I really encourage people to give it a whirl, take it for a spin. Even in the browser with simply Scala.com, yes, it's a little out of date, but it's plenty good enough to get started with. Just to literally type in some code and try it out. But download it and install it if you want. Hey, I'm local-ish. I live up in the valley, and I'm at all sorts of other meetups in the area, and I'm always happy to talk to folks who are curious. It's not going to break my heart if you don't switch to Scala. I come in peace. I'm not a religious zealot. I have been using the language recreationally for about 4 years, and I've been using it on the job for about a year and a half. I'm really happy. I have to be honest. I'm really happy not to be a Java developer anymore. I think that's